We did a problem before where we considered a boy going down a water slide. Here's my boy represented by a circle. And we talked about the thermal energy that was created, and we used conservation of energy to kind of figure that out. Now, in that, we considered the system to be the boy and the slide, which we had to do because the thermal energy was created by friction between the slide and the buoy, and so the slide and the buoy had to be in the system because the frictional force has to be, the thermal energy is going towards both those objects. But we chose that the work done by gravity, the Earth through gravity, to be external to the system. Well, what if we changed this and said it is also the Earth? Our system includes the Earth too. So that means the force of gravity is inside the system. What does that look like? So if we do work external equals our change in kinetic energy plus our change in thermal energy, well, our system now includes the Earth, and that force is an interaction, and we can call interactions potential energies, and we give that a symbol U. And specifically for the force of gravity or interactions via gravity, we call it a gravitational potential energy. And because of that, there's nothing else left to act on our system. We've included everything acting on the board, the slide, the Earth, all through gravity. So there is no external work, which means these values, the sum of these values, shouldn't change. Now, it does mean that the values themselves could change, converting one type of energy into another. But the point is sometimes we can just consider the gravitational potential energy rather than trying to calculate the work done by gravity. And I'll leave the derivation for the text, but what we end up with is a definition that gravitational potential energy, UG, is equal to the force of gravity times the vertical position. Now, something that is important is that the vertical position, or that our coordinate needs to be measured upward as positive to be able to consider this. Because the higher something is up, the more potential it has to fall, or the faster it will go as it goes down. And so the increase in kinetic energy must be followed by a decrease, or caused by a decrease in potential energy. So here we have to choose our coordinate system to be pointing upward. Okay. For an extension off of this, there's all sorts of different potential energies. And we're going to cover in this chapter, we're going to cover gravitational potential energy, spring potential energy, and basically the important thing is potential energy is an interaction energy. Oops, forgot my T. Interaction. Sorry, an interaction energy. So it requires multiple objects. So in this case of gravity, it's the energy between the buoy and the Earth through gravity. On a spring, it'd be the molecular bonds being squished or stretched in the spring. There's chemical potential energy, and that's the energy that's stored in chemical bonds getting ready to be broken up to provide energy in different ways. There's lots of different types of potential energies. But again, we'll focus in this chapter on gravitational potential energy and spring potential energy, where we can actually have relationships for them. Spring potential energy has, we'll call it USP, is 1/2 K delta S squared, where delta S is either the stretch or compression of the spring, and K is the spring constant. Okay, so we'll have these two relationships to work with. But whenever we consider the potential energy, it is an energy of interaction, which means the objects that are interacting must be inside the system.